Hi there, students. In this video, we're going to explore where the quadratic function actually comes from. Let's look at these squares. What do you notice about them? You may have noticed that they increase in size. Let's look at exactly how. The first square is a 1 by 1. The length is 1, the width is 1. Recall that area is length times width. So the area of the first square is 1 times 1, 1 square unit. The second square is a 2 by 2. The area, therefore, is 2 times 2, 4 square units. We can see that it's 4 square units because there are 4 tiles. The third square is a 3 by 3. The area is 3 times 3, 9 square units. The fourth square is a 4 by 4. The area is 4 times 4, 16 square units. So now we can see exactly how many tiles are added to each square in order to cause them to increase in size. From the first square to the second square, we went from 1 to 4 tiles. That is an additional 3 tiles. Then we increased from 4 square units to 9 square units. That is an additional 5 tiles. We can see the 5 tiles here are the orange tiles, 1, 2, 3, 4, 5. Then we increased from 9 square units to 16 square units. That is an additional 7 tiles. Then we can look at the rows and columns. From the first to the second square, we added 1 row and 1 column. That is plus 2 to the dimensions. Then we added another row, another column, another plus 2. We can see that we have some common differences here. 3 plus 2 is 5. 5 plus 2 is 7. This is a concrete example of the quadratic function. Now let's represent what happened to the squares in a table of values. When the side length was 1, the area was 1. When the side length was 2, the area was 4. When the side length was 3, the area was 9. When the side length was 4, the area is 16. Let's see how the area has changed as the side lengths increase. From 1 to 4, we added 3 tiles. From 4 to 9, we added 5 tiles. From 9 to 16, we added 7 tiles. These are called changing differences. We can see how these numbers change as well. From 3 to 5, we added 2 to the dimension, 1 column and 1 row. From 5 to 7, we also added 2, 1 column and 1 row to the square, 1 column and 1 row. This here is called common second differences. Quadratic functions always have common second differences. Let's see how the quadratic function looks on a graph. We can use this table of values to plot points on the graph. The x-axis represents the side length. We're going to focus on the positive side since we cannot have negative side lengths. Let's look at the positive side first. When the side length was 1, the area was 1. The y-axis is the area. So we can match it up. When the side length is 1, the area is 1. When the side length is 2, we can go up to the red point and go to the y-axis. The area was 4. When the side length is 3, the area is 9. When the side length was 4, the area was 16. When the side length is 5, the area will be 25. When the side length is 6, we're off the graph, but we can see that 6 times 6 is 36. The benefit of displaying the data on a graph is that we can see the trend that the area is increasing, and we can find lengths that are greater than the ones shown in the concrete example. We can show areas that are larger than what we displayed on our table of values. In this particular example, we're only looking at the positive. However, there are other real-world examples where we might use negative numbers, and in that case, the graph would be symmetric and would look like this. This is called a parabola. We'll explain this negative side in just a moment. Let's look at how this table of values can help us find an equation. Anytime there's a pattern in math, mathematicians like to create a formula to show the pattern for any number. So, when the side length was 1, the area was 1, because 1 times 1 equals 1. We can also write 1 times 1 as 1 squared. When the side length was 2, the area was 4, because the length and the width of the square is 2. So 2 times 2 is 4. We can express that as 2 to the power of 2, because there are 2 2's, 2 squared. When the side length was 3, the square was a 3 by 3. 3 times 3 is 9. We can show that as 3 squared. When the side length was 4, 4 times 4, we can express that as 4 squared. But what if I wanted to build bigger squares? Any number of squares, 5, 6, 10, 100, we can use the letter X to represent any size square. The side length is X, any number we choose. No matter what number we choose, because it's a square, the length and width will be equal, and we'll be multiplying the same number times itself, X times X. I used a dot so that we would not confuse it with the letter X. X times X can be expressed as X to the power of 2. This leads us to the equation of a quadratic. The equation of a quadratic is y equals x squared. X stands for the side length, any number we can use for x. Because it's a square, there are 2 sides, the length and the width. There are 4 sides, but 2 dimensions, length times width. If we multiply length times width, we will get the area of the square. We can use this equation to find the area of any square. This is considered the abstract concept of quadratic functions. Now with this formula, we can explain why we have a negative side to the graph. Y equals x squared. I can pick a negative number. Y equals x squared. If I pick negative, negative 1 to the power of 2, which is negative 1 times negative 1. A negative times a negative is positive. So that would be negative 1, comma 1. Negative 2 times negative 2 matches up with 4. Negative 3 times negative 3 matches up with 9. So then this gives the shape of the entire parabola. This parabola is used in the real world for rockets, missiles, even if we look at it reflected, this can represent kicking a soccer ball, throwing a football. There are many practical uses for a quadratic. Thanks for listening and hope this helps you.